So using this problem from the multiple choice as a quality example here of momentum in 2 dimensions, I'm going to make a quick change to this. I can't stand the fact that they've used x and y for these, considering I'm going to be talking about the dimensions as x and y. So I'm going to call this object A, and this one object B, and this is the direction A goes after. And they're asking us which way does B go. So, pardon me while I deal with something. This is before, right here. This is before, and this is after. Now, what they're not showing you in this picture, in the after picture, is that, here we'll make object B blue, is that object B, we don't know what it does. Does it stay right there? Does it move down and to the right at various speeds or angles? We're supposed to pick one of those. So if it stays there, it would look like that. If it was down into like something like that maybe, but that's what they're looking for. So they want to know what. Now, this is an example. This is an example of a problem where the initial momentum isn't 0. Take a moment. If we assume that, I think it's safe, let's just make it easier on ourselves. They don't give us the mass, but they do say they're the same mass, right? So let's make the mass of both of them 1 kilogram. Seems to me that if I use 1, it's going to make my life a lot easier. Yeah, if they're the same, it's not going to make a difference in this case. So, how about this? And we're going to discuss it a little bit, and we're going to talk about how you could have eliminated a lot of these. So first of all, the momentum before, the total momentum before, is all in just object A, and it's 10 kilogram meters per second, and it's going just to the right, correct? After the collision, when you add up all the momenta of the 2 objects, what is the final momentum going to be? It's got to be 10 kilogram meters per second to the right. It has to be the same. Because conservation, all the forces are internal. It's just between the 2 objects. Now, what's interesting, though, is it's not going to look like 10. Like, for example, I'll give you the basic idea of what's going to happen. Here, that vector looks like that. Cool? Now, I'm going to take this. I'm just going to do this. I'm going to go object A went off like that, right? Let me just extend that a little longer. There we go. Which way did object B go? Well, it went, we'll do it in green. It would have gone down this way, I'm thinking. Maybe like that. Now, that's not going to be great either. Here's what I know. This vector combined with this one, when I'm done adding those vectors, what should I have? I should have 10, what I started with. See, there's more than one way to get that 10. You could have 10 to start with, or you could have 2 vectors. Let's make, here, we'll make them up on this. So if I go here, and I go, make that a different color. There we go. So if I take this vector and I add it to the blue one here, and let's see, let's do this. What's its x component? About that big, right? Okay. So I need one that has a similar, well, let's just do it this way. So what about blue's x component? It's about the same, right? If you add those 2 together, you get this. Now what about their y components? This is one of the... How do we know they have to cancel out? What was the y momentum before? See, all that momentum was in which dimension? All right, it was in the x. So the initial x momentum was 10, but the initial y momentum was 0. So these two, after the collision, have to cancel each other out. So that's what makes it more complicated, because you're adding two vectors, but that's more complicated than just, adding this 5 and 2 or whatever. It's not that simple. So we have to go components and everything, but I think we've hit on the key to this problem. I need these two y components to cancel out. So let's go back to our choices. Remember, you're considering this is one vector, up and to the right, and then, by the way, can we rule out this one, please? Yeah. Right? I mean, if I add this vector here to nothing, I get this. Is this the same as what I started with? No. So, no. I mean, think about if something hit that and then we're not talking about things that are nailed to the ground. Why would it stay there, right? All right. Okay, so our choices are these three. Anybody got a reason why they can rule out another one? Tammy. Why can you rule out D? So she points out that this one here has the same angle. So in order to have the same y component, you'd need if you had the same angle, you'd have to have the same speed, right? But it's got more speed. So its y component would be bigger than this one, wouldn't it? So, gone. I agree. I'm ruling that one out right away. Well, second of all. Okay. Anybody in the current class think they can rule out another one? We can rule one out that we can guarantee must be too small. All right, so it kind of gives it away, but why is B too small? Could you explain to somebody why that is? What does lowering that angle to 37 do to the y component? It makes it more horizontal, so it makes the y component smaller, doesn't it? So changing the angle to 37 reduces the size of a y component. All right? Think about it. If you're struggling with that, let me just point that out. So if I take the same arrow here, it's all on the y, right? Now I'll put some axes in here. So here, that's like maximum all y, correct? As I take that vector, I got this. Screw it. Hold on. We're going right here. We're going to use the mouse. The boards aren't helping me here. So as I take that vector and I move it, what happens to this y component right here? It used to be down to here, didn't it? All right, down in here somewhere. Now it's getting smaller. As I rotate that farther and farther, that y component is now, for example, only, I'll use a different color, is only this big, right? From here to here. So as you get, that angle gets closer to the x-axis, the y component gets smaller. So, but the speed on this one also got smaller, didn't it? So you're getting a smaller part of a smaller vector. You have no hope of canceling the y one and the other. Now, you could get a calculator out and do this real quick. What would, let's do this. If we just use 1 kilogram, that means this y component would be 8 kilogram meters per second worth of momentum times the sine of 37. What would the y component of this one be? 6 kilogram meters per second times the sine of 53. If you punch those both out on a calculator, they should come out to be roughly the same. But you shouldn't have, in this case, you shouldn't have to go to the calculator to get it. 6 times 53 sine equals about 4.8. And 8 times 37 sine equals 4.8, about that. So one's up, one's down, so they should cancel out. Make sure you're not in radians and that you know how to use your calculator.